Hello, my name is Scott Miller. This is Jake Whelan, and for our senior project, we developed a system to optimize the warehousing of palletized inventory for the local company iFixit.
At iFixit, the process for warehousing palletized inventory is inefficient. This process is not considered expensive, but is labor and time intensive. However, in the initial state, there are no baselines for continuous improvement. Because of this, success criteria for this project were mainly determined by qualitative results. The industrial engineering curriculum provided us with several tools that we used in developing a solution to this problem. Specifically, process improvement fundamentals, engineering economics, human factors, supply chain management, and facilities planning and design classes were important in developing an optimal solution.
iFixit has two warehouses, Facility A being the main warehouse with shipping abilities, and Facility B being used purely for inventory holding. Facility A can hold up to 31 pallets, while Facility B can hold up to 90. iFixit currently uses whiteboards to track inventory at each warehouse. At Facility A, iFixit maintains an updated whiteboard of both warehouses. iFixit uses these whiteboards and paper facility layouts, along with each shipment's packing list, to determine locations for newly received palletized inventory. This process typically is conducted by two managers and takes approximately 1 hour. Once pallet movements are made, the new layout must be recorded on a paper layout. Four employees are in charge of maintaining accurate information, but each employee has different handwriting, some more legible than others. This makes understanding layouts without all employees present difficult. Many problems can arise from this lack of a standardized process.
The initial planning of this project included the target inventory level calculations for Facility A and the development of a zoning system. In the do section, we used 5S principles at Facility B to prepare the zoning implementation. Along with 5S, we created a visual management system based on our 5S plan to enhance worker experience involved with Facility B. To check these systems, we made spaghetti diagrams and conducted time studies. As this project is in the spirit of continuous improvement, we analyzed several qualitative benefits. Acting on these prior tasks involves standardizing and cycling zones until they are accurate, as well as fine-tuning the use of mixed pallets in the zones.
The first step we took was developing optimal inventory levels for each of the 19 commonly palletized SKUs at Facility A for 1 month. We did this using a formula that sums the usage of a product over its lead time with the standard deviation of demand for each product times its desired service level. Because iFixit doesn't want a stock out of any of these products, the service level was said to be 99.98%. By converting the target inventory levels from the quantity of each SKU needed each month to the equivalent number of cartons needed and the percentage of a pallet needed, a balanced group can be made. Ultimately, 3 groups were formed, each consisting of 16 pallets. 14 of these pallets consisted only of one type of product, while 2 pallets are made of a mix of multiple products. As a rule of thumb, products of which 75% of a pallet or more would be needed for 1 month of inventory would account for at least 1 pallet in the group. If less than 10% of a pallet was needed, the product would be moved only on the carton level. Between 10% and 75%, pallets would be delegated to a mixed pallet. Each group was dedicated a zone within Facility B and will be named by the month in which they will be pulled. If the system were to be implemented today, Zone 1 would be named March, Zone 2 would be named April, and Zone 3 would be named May. When March is pulled, Zone 1 will be replaced by a new zone named June. Every time a group is needed, a section of the warehouse is pulled. The section chosen rotates as each previously pulled section is replenished by newer stock. All additional space will be used as a queuing area for pallets waiting for a spot to free up in a higher ranking zone or for miscellaneous rarely held pallets.
Steps were taken to implement 5S principles at Facility B. Initially, a coordinate grid system was developed to help a user in identifying where a specific pallet is located within the warehouse. Facility B was separated into 5 general areas: port, starboard, room, overflow, and middle. Both the port and starboard areas have 4 rows, which are labeled A, B, C, and D, with A being the closest row to the center of the room and D being the farthest. Column numbering for port begins closest to the warehouse entry door with column 1 and continues to column 9, while column numbering for the starboard side begins with column 3 and continues to column 13. This is done as such to have column numbers mirrored across the warehouse. Port column 3 is directly across the warehouse from starboard column 3.
A visual management system was designed using Google Sheets to provide an improved visual assisting in pallet location. First, a digital version of the current Facility B map was rendered. The grid system was laid out over this map and zones were outlined. Drop-down lists were placed in each pallet spot, which contained all potential pallet types. Each pallet type was given a different formatting color, which helps to quickly identify where each pallet is on the map. Because the system is based in Google Sheets, it is accessible anywhere an employee has access to the internet. This eliminates the need to be in either Facility A or Facility B to know what is in each warehouse. Once a user inputs the data into the VMS, the pallet locations are pushed to two spreadsheets, Zone Contents and More. Zone Contents counts the number of each type of pallet in each zone and compares it against the proposed group total. This sheet helps to dictate where newly received pallets should be directed. The More sheets provides a cell-by-cell description of what is in each pallet spot. Additionally, this sheet allows a user to add notes to each pallet. Potential notes include the purchase order attached to the pallet, whether a pallet is to be used for kitting, or if products are ready to be sold.
As a result of the zoning system, total worker movement will be reduced and centralized. In the initial diagram on the left, the workers' movements needed to remove a set of pallets from Facility B and transport them to Facility A are tracked. The red lines represent movement without a pallet, while green lines represent movement with a pallet. The worker is required to move around to different areas of the warehouse to retrieve all of the needed pallets. This sometimes involves moving pallets out of the way in order to get to the needed pallet. On the right is a spaghetti diagram of proposed zoning system. This system does not require the worker to move unnecessary pallets and reduces the amount of searching needed. The worker's motion will be confined to the zone that is being pulled, thus reducing the variability in each movement. A time study was done to compare the pallet movement time in the initial state to the proposed state. The total time in the proposed state is approximately 6 minutes quicker than that of the initial state. A 7-pallet load is not standard, so time per pallet was calculated for scalability. A reduction of roughly 52 seconds was saved per pallet in this operation. In the new zoning system, a standard pallet load is 16 for 2 loads of 8. A 3-minute operation can be measured as dollars saved per pallet and work minutes saved per worker. In order to scale these savings to an entire pallet and yearly cycle of 12 loads, a model was made. A total of $165.67 can be saved in total labor costs over the course of a year, once the zoning system is fully implemented.
On top of the quantitative savings from the implementation of this process, qualitative gains justify this project. Having the entire warehouse layout on a cloud-based software allows for the data to be seen at nearly any time and place. Updating pallet locations can be done quicker and can save an estimated $38.73 annually. Being able to update the VMS using a phone reduces the uncomfortable positions workers must assume to record pallet locations. An estimated $300 can be saved annually due to the reduction in time needed for planning. Preparation in the proposed system simply cross-references packing lists with the zone contents page. Consistency is guaranteed as pallet callouts cannot be misprinted or misused because of the drop-down system. Above all else, the work we have done provides a platform for continuous improvement. Target inventory levels, group contents, and zone layouts can be fine-tuned and updated. Additionally, the system can be implemented into the database used by iFixit, which would allow for more complex inventory tracking and planning.
In conclusion, we developed target inventory levels for Facility A. This allowed us to create the contents and layouts of the zones in Facility B. We made a visual management system in 5S Facility B. Annually, we estimate a savings of $504.40, but qualitative savings that provide a baseline for continuous improvement allow for more valuable returns in the future.